Okay, today we'll start with day 2 of lessons on thermochemistry, and we'll start by explaining the enthalpy change and how do we calculate it, why do we calculate enthalpy change, and then we'll move to more questions and examples and applications of the enthalpy change. So the very first thing that we have to explain in today's class is why do we calculate enthalpy change and why don't we calculate just enthalpy of a reaction. So what do we have to keep in mind here is that internal energy that is into the bonds of the chemical reactions can be transferred when a reaction is happening in the form of heat and energy. Both of them are very difficult, like especially the energy is very difficult to calculate on this case. And when we are talking, if we want to calculate the energy per molecule or per bond, it is very difficult to calculate it immediately. However, what is neat about those two terms? So we have heat and energy, or work done, heat and work. What is neat about them is that work is the energy that is transferred to the motion of an object. So when an object is moving, the volume is increased or pressure is changing, then work is done on it. And heat is so this is a motion of object. And heat, on the other hand, is the motion of atoms and molecules. What we have to keep in mind here is that the change of energy is independent of pathways. So it doesn't really matter what is the path that the object is obtaining. What is important is that what is the final initial state and the final state. This kind of principle in which we use, especially on energy and work, is known as the state of function, which means that it doesn't matter what is happening in between, but what is important is what is the starting state and what is the ending state. This makes it very easy for us because let's say that a great example is if you want to measure the volume of the ocean in Earth, every ocean in Earth. It is very difficult. You cannot measure it. You literally cannot measure it. However, if you add 2 liters of liquid into the ocean, then you know that the change of volume in the ocean is exactly 2 liters. Okay, so you cannot measure the initial volume, but you can measure the change of it. The same concept is with the enthalpy. It is very difficult to measure the enthalpy of a state, but you will be able to measure the enthalpy of the change between the state, the final and the initial. Because in this case, math is very simple. It is whatever is the amount of ending state minus the amount of the starting state. So what is important here is that what we really need is a state of function, which is final initial, a state of function based on loss or gain of heat in chemical reaction, based on loss or gain on heat in a chemical reaction. And this is known as the enthalpy. Okay, so the enthalpy is the internal energy of the system. Enthalpy is known with letter H, is internal energy of the system plus the energy that is required to sort of shove the surrounding out the way to make room for the system pressure and to open some room for the system of pressure to on the change of pressure and the volume. So this is impossible to measure. This is impossible to measure. Therefore, what do is we are not interested on what is the total enthalpy. This is the total enthalpy of the system. We are not interested on this. But what we are interested, and it is impossible to measure, what are we interested is we want to know how much is going to change as a state of function. So how much is going to change as a state of function. As a state of function. So what we are interested actually is delta H, which is heat plus work plus change on pressure and volume. Now, here we have two biggest assumptions of what we are doing. First of all, is that the pressure is staying constant. So and it's fair assumption to do. Pressure is at the surface of the earth when you are completing a chemical reaction, it is going to not drastically change to affect it. So this is the first assumption. Pressure is constant. Making this term here as delta or P times delta V. Okay. And the second assumption is that the work done is the opposite, the work is the opposite of P delta V. So when we rewrite this equation here, what we will have is the change of enthalpy as a state of function, initial final, will be equals to Q minus P delta V plus P delta V. And this is canceled out. So the math is becoming very simple. We are saying that the change of enthalpy is equal to the heat gain. Change of enthalpy is equal to the heat gain or lost, depend, by the system, the chemical system, okay? So all this explain why are we not able to calculate the enthalpy of a system, but we are able to calculate the change on enthalpy of the system. And now guess what? In a chemical reaction, what do we have? We have products as the final state and reactants as the initial state. So now the change on enthalpy is of a system will be whatever is the enthalpy of the product as being the final state minus what is the enthalpy of the reactant being as the initial state. So, I always say that delta is final minus initial. So now, this change of heat that the system is undergoing is going to be either absorbed or absorbed from or released to the surrounding, and this brings us into that we know as the colorimeter. Okay, so again, this slide here explains the fact that we are not able to calculate the enthalpy of a system, but we are able to calculate the enthalpy change of the system. And the biggest assumption here that we are doing is that the pressure is not changing. The pressure where you are completing the reaction is not changing, is not having any effect, and that work done to kind of, create some way to make room for the system of the pressure and the volume is equal to the work done in the opposite sign, then those two will cancel out to each other. Those will cancel out, which leads us into the conclusion that the change in enthalpy of a system is equal to the heat gained or lost by the surrounding. Okay? Let's take a look at this graph that you see here, in which we have as the reactant, we have zinc and hydrochloric acid that are producing or reacting together to produce hydrogen gas and zinc chloride. So now, what is happening here is that the red color, the red line, is representing the potential energy of the bonds, the chemical bonds, or the sum of potential energy that the chemical bonds have when we have the reactant as zinc and hydrochloric acid, and then as a product of hydrogen and zinc chloride. And the blue color is representing the kinetic energy of the surrounding. We mentioned it even on the first couple of videos, where we were saying that the heat is a direct proportion of the kinetic energy of the surrounding. Heat or temperature is direct proportion of the kinetic energy of the surrounding. So what is happening based on the conservation law of energy is that the energy cannot be destroyed, cannot be conserved, but it's transformed from one form to the other. What is happening here in our graph is that the potential energy of the chemical system is decreasing, the same decrease of the potential energy is having will be going to increase the kinetic energy of the system. So as the potential energy of the system is decreased, then the kinetic energy of the surrounding is increased, which will result into a higher heat, which will result into warming up the heating of the surrounding, or higher temperature of the surrounding. So this graph here is a direct relation of the conservation law of energy, and how do we use this conservation law of energy in the chemical reaction when we are designing the colorimeter? Because what is happening in the colorimeter is that the potential energy that is changing in the chemical reaction is reflected in the surrounding of the uh, colorimeter, which in most of the cases is water. Okay, makes sense? Okay, so now when we have a change on enthalpy that is negative, then we have exothermic reaction. So let's take a look at it, what it is. Let's suppose that we are graphing here a graph that we have some products here. I will just make products in green so that we can see and work with both cases in the same graph. And what we have here is a certain potential energy of those products. So this is EP. Potential energy, again, as we said, it is the energy that is stored into the bonds of the chemical compounds. Okay, so now we are saying here that if we have an exothermic reaction, then the enthalpy change is negative. First of all, why is it negative? Because the enthalpy of the reactant is less than the enthalpy of the product. Okay, what is happening in terms of where is this change going? This change is going to the surrounding. So as a result of this, what will happen is that the products will be somewhere in here. Products. This one here is known as the exothermic reaction. Okay, exothermic reaction. Why? Because what is happening is that you are releasing the energy, and we always treat it from the a point of view of the system, of the chemical system. So the chemical system, as a result of the reaction of the products, is releasing the energy to the surrounding. What is happening as a result of this is the temperature, the kinetic energy of the surrounding is increased. Or what else do we notice is that the temperature of the surrounding is increased. This change of temperature is going to the surrounding, which in the case of the colorimeter is majority is water, majority of it is water. So therefore, what will happen is that the temperature of the water will increase. However, when we have that the product is absorbing the energy from the surroundings. So the enthalpy of the product is greater than the enthalpy of the react. Here we should have reactant. Sorry. Here we should have a reactant. Sorry. The enthalpy of the product is greater than the enthalpy of the reactant. How does that look like into your diagram? Is that the enthalpy, the products are absorbing the enthalpy or are absorbing heat from the surrounding, and then they are moving to the products, Then this type of reaction is known as the endothermic reaction. And what is happening during endothermic reaction is that the kinetic energy of the surrounding is decreased, which will result into less heat on the surrounding, and the temperature of the surrounding will be decreased as well. So feel that in the case of the calorimeter, you will feel that the temperature of the water is lower than before the reaction. And this change based on the conservation law of energy is going to be absorbed from the surrounding. So if in this case, what do we have? It is released to the surrounding. On the other case here is absorbed from surrounding. Make sense?